Hi everyone, my name is Rachel, and today we'll be talking about Part 1, PN Junction Important Graphs. Here we see a PN junction at equilibrium, meaning that there is no externally applied electric field or voltage onto this PN junction, where we have P-type on the left and N-type semiconductor on the right. We can see that this is a carrier concentration versus X position graph, where we can see that when we have a P and an N right next to each other, at equilibrium, there's a space charge or depletion region W width that is formed, where the P-type dopants have their holes diffused to the N-type, leaving behind these negative, as shown in blue, dopants. And then the N-type have the dopants have electrons diffused to the P-type region, leaving the positive dopant nuclei. And so that's why we have negative and positive. You can see that there are 5 negative and 5 positive, and so overall in the space charge region there is a neutral charge. And you can also notice that in the P-type they have a larger section of the width compared to the N-type for the space charge region, and this is because the P-type is less doped than the N-type, so we have to have more of this width region in order to get more negative charges that will balance out with the positive charges, and therefore this total width of from here to here is our width of our depletion region, also known as the space charge region. And so this is what it looks like at equilibrium. There are a few graphs that are important to understand, especially at equilibrium, in order to understand how devices like solar cells work where they are not at equilibrium, because we have an external voltage or electric field that is being applied that changes the equilibrium behavior. And so we have here, first we need to understand where the electric field is coming from. We can see that because the positive charges are on the right and the negative charges on the left, if you have a point charge like an electron, the electron will travel from positive to negative, and so that is why our electric field is going to the left direction from positive to negative. With this, we can then move on to the charge density to understand how are the charges distributed throughout this PN junction. And we can find that as we extend these lines in order to remind ourselves where the space charge region is, we look at the carrier concentration graph and find that because the P-type region on the left before the space charge region is charge neutral, we have a line here showing 0 charge. When we go to the negative area, we have a negative rho or charge density. And then continuing on, we have a positive charge density as we go towards the N-type. And then 0 again, since at the right, beyond the charge region, we have a neutral charge N-type. And so that's why we have a 0 rho. You can see that the graph is a flat line at the charges because you have a constant charge density as we continue on and increase x. Using this, we can then go on to finding what the electric field graph is, and we use the Poisson equation where we find that dE dx is equal to rho of x over epsilon. And we can find that rho is the charge density, which is equal to Q times the carrier concentration of the P-type P minus N, which is the carrier concentration of N-type, plus the dopant concentrations of Nd minus Na, where Nd is the positive nuclei dopants and Na is the negative dopants. And so with this equation, we know that rho of x, the sign of that will determine what the sign of the slope is for dE dx. So with that, we know that from here, we see that rho is 0, so therefore the slope is 0, so we have a flat line. Then because there is a flat line graph subsequently for rho of x here, we know that integrating this would be a linear line. Since this is a negative charge density, that means the slope of the electric field will also be negative, and so we have a downward sloping line. At this region, we have a cross point where we see that it's not negative anymore, it's going positive, so a positive slope for electric field, and also because the line is flat, that means this is a linear line going upward for the electric field. And then finally we have 0 for the rho of x beyond the region of the space charge W, and so we have a 0 slope for the electric field. The point here is 2V0 over W0, where W0 is the space charge region width at equilibrium and V0 is the voltage at equilibrium as well. Then we can move on to the voltage graph, where from the electric field graph we can use where the electric field is equal to the negative of dV over dx, and so we can use the equation and rewrite this as V is equal to negative of the integral of E of x dx. And so if we integrate the electric field graph and negate it, we can then find the voltage graph. And so repeating this procedure, we can look at the left where we see that the electric field is flat, is 0, and so the voltage would also be 0. There's no area under the curve for the electric field, so 0. And then when we go here, we find that the area is increasing for the electric field graph, and we are at a negative electric field. And so because we have a negative electric field as well as increasing area, that means we have a overall positive voltage. You can also look at it like the electric field is negative, and so dV dx would be positive since we have this negative sign. And so that's why our voltage graph is increasing upward. And we find that because the area from this cross point, we have that here, as the area is increasing, we have less and less area that is increasing as we go and increase x, and so this graph slows down, but it's still positive because we have a negative electric field, and then you multiply that by a negative, and that would be a positive dV dx, so a positive slope while we're increasing slowly the area, and then the graph flattens out because we don't increase any more area. Instead, we are at a constant electric field, and so our dV dx is going to be 0, it's not changing, so it's a flat line. And so overall, these are the important critical graphs for PN junctions that are important to understand, especially because at equilibrium is very different from when you not have at equilibrium, where you apply an electric field or voltage, which is the case for many devices that are operating, such as solar cells. When you put it out into the sun, you start to have different kinds of behavior and different carrier concentration behaviors that are different from these graphs. And so it's important to understand what these graphs look like at equilibrium to understand the behavior of when these devices begin to operate with these PN junctions applied with an electric field or external voltage. Thank you for listening. If you have any questions, please comment down below. And if you have any suggestions for next videos, please also comment and share them below. Thank you.